welcome to Physical Geography 100 lecture podcast series. I'm Brian Krause, your instructor, and today we're going to discuss plate tectonics. In this mini lecture, like all mini lectures, I'm not going to cover all topics or ideas presented in the text. Rather, my aim is just to highlight a few key ideas and then discuss them in a bit more detail. So on that note, let's get started. At the end of this lecture, you should be able to compare and contrast the geological features of the three types of plate boundaries, explain the age of seafloor rock and the magnetic reversal, and finally, explain the relationship between earthquakes, volcanoes, and plate boundaries. The first question that we should ask is, what are plates? And the Earth is broken up into different plates, and the lithosphere is broken up into different sections called plates. And those sections are going to be either made up of oceanic crust or continental crust. And when these two types of crust interact with one another, they're either going to slide side by side, or they're going to pull apart from each other, or they're going to come crashing together. In this lecture, we're going to discuss how they pull apart and how they crash together. Plates that slide side by side, or also called transform boundary plates, will be discussed in a later lecture podcast. The first type of plate boundary we're going to discuss is divergent plate boundaries. Divergent just means pulling apart. This means that they are moving away from each other. Divergent boundaries are also called spreading centers because seafloors spreading occurs at these boundaries. And there are two different ways you can get divergence on the planet. You can either have oceanic divergence, which is called oceanic ridges, or they can have continental divergence, which is called continental rifting. There are some geological features associated with divergent boundaries that you should be familiar with. Here, crust is created, as well as underwater mountain ranges and volcanoes. Earthquakes occur here as well, but these earthquakes are not nearly as violent as with subduction zones, which we will discuss in a later portion of this lecture. So here in this figure, which is out of your textbook, is a classic mid-ocean ridge. And we can see that this is two divergent plates. They are pulling apart from each other. They're moving in opposite directions. And here's an artist's rendering of the Atlantic ridge might look like, which is a mid-ocean ridge in the Atlantic Ocean. And this big crack down the middle of the Atlantic is separating North America from Europe and from South America from Africa. Mid-oceanic ridges are found underwater, so your plates are pulling apart underneath the ocean. Where the crack in the ground is found is where your rift is going to be filled with magma. And this is where the youngest rock is found. This is also the longest mountain range on the planet. And as mentioned earlier, this is where the seafloor spreading occurs. The mid-ocean ridges of the planet are connected to form a single global mountain range. They just so happen to have different names in different locations. So in the Atlantic, it's called the Mid-Atlantic Ridge. In the Pacific, it's called the East Pacific Ridge. And in the Indian Ocean, it has a couple of names. There's the Southwest Indian Ridge, and the Central Indian Ridge, and the Southeast Indian Ridge. So as you can see, it's the same mid-ocean ridge. As I mentioned, they're connected. They just have different names for different regions. So scientists needed some kind of evidence to support this seafloor spreading. And the first one is the age of the seafloor rock. Because magma is found right at the ridge, this is where the crack in the plate is, and that the place is where the youngest rock is going to be found. So young rock is found right at the rift, and as you get further and further out from that ridge, the rock gets older and older and older. So here's a map from your textbook illustrating this. So the youngest rock is in the dark red, and the oldest rock is in the dark green. So we can see right at these mid-oceanic ridges where the seafloor is spreading, we have a very young rock because this magma is rising up to the surface. The next evidence is the reversal of magnetic polarity. Our Earth has a magnetic field, and this is caused by the fact that our Earth rotates and has a liquid iron and nickel core, and it is going to rotate with the Earth and create that field. We know that magma comes to the surface. It has these magnetic minerals. What scientists have determined is that these minerals in the rock, as they solidify into rock, will lock in that polarity at the time of formation. So most of the rock on Earth has this dominant magnetic north polarity with the minerals. But scientists have found certain areas on the ocean floor that have dominant south polarity, which give an indication that one time our magnetic field has flip-flopped and has turned upside down, where instead of having dominant magnetic north, we have had dominant magnetic south. So this has provided evidence that rock itself has possible magnetic reversal with our poles. Over the past 330 million years, scientists believe we have had about 400 of these reversals. The next type of divergent boundary is called continental rifting, which is where two continents are splitting apart. They're again pulling apart from each other. A modern example of this occurring is the East African Rift. And here is an excellent example of the initial stage in the breakup of a continent. Tensional forces have stretched and thinned the crust, allowing molten magma to ascend. Whether the rift will eventually result in a breakup of Africa is certainly a topic of further research. When we talk about convergent plate boundaries, we're dealing with three different types: ocean to continent, and continent to continent. So let's take a look at some of these geological features, and let's first begin with ocean to continent. With ocean to continent convergence, the crust is destroyed here through a process called subduction, and we'll get into subduction in more detail in a moment. You also have mountain ranges at these locations, and then some of them are going to be volcanic. You also tend to get very strong earthquakes, and you tend to get offshore trenches as well. Here's a diagram from your text on what ocean to continent convergence looks like. Earth's convection cells are going to take the oceanic crust on the left, and they're going to cause the continental crust on the right to collide with one another. Because of the difference in crust density, the oceanic crust is going to move underneath the continental crust. The oceanic crust is more dense than the continental crust. Where the oceanic crust moves under the continental crust, this is what is referred to as subduction. And during the subduction process, there is a tremendous amount of friction, so you get some very strong earthquakes along these subduction zones. As the oceanic plate gets deeper into the earth, it gets hotter and hotter, and eventually it gets hot enough to melt. And depending on the environment, this magma ascends to the surface and gives rise to volcanoes. Where these two plates interact is called a trench, and tend to be some of the deepest points on the earth. So let's take a look at some of where these features can be found. First off, in North America, you have the Juan de Fuca plate that is subducting under North America. You will have big earthquakes, mountains, trenches, and some of the mountains are quite active in volcanism. You'll get the Cascade Mountain Range down the west coast. You get the same features with the Coca plate, where it is subducting under the North America plate and the Caribbean plate. Again, you get the same features with the Nazca plate. What is important about the Nazca plate subduction near the South American plate is that the Peru-Chile Trench, which is the location of the biggest ever recorded earthquake back in 1960 at 9.5 on the Richter scale. There is also a very large mountain range called the Andes Mountain Range here as well. Now the second type of convergent boundary is ocean to ocean. Again, you get some of the same exact features. Crust is destroyed here through the process of subduction. Mountain ranges are built. Some of the mountain ranges can be volcanic. You have very strong earthquakes and some trenches. So what's the difference between ocean to ocean and ocean to continent? Let me show you. So here you have two oceanic plates converging, one descending beneath the other. The only difference is that the volcanoes form under the water. If the subduction is sustained, it will eventually build this chain of volcanic structures large enough to emerge as islands called volcanic island arcs. So let me show you where some of these features are found. The Aleutian Islands are an ocean-to-ocean convergence. The Japanese islands are ocean-to-ocean convergence. And here you have the Tonga Islands, which is an example of a relatively young volcanic island arc caused by ocean-to-ocean convergence. The perimeter around the Pacific Ocean is called the Ring of Fire, or the Pacific Ring of Fire. Very simply because of some of the world's largest volcanoes exist around the perimeter of the Pacific Ocean, and some of the world's strongest earthquakes have occurred around the perimeter of this Pacific Ocean. Because of such violent subduction, violent earthquakes, and big volcanoes, it's referred to as the Ring of Fire. The third type of convergent boundary is called continent to continent. Here, continental crust crashes into continental crust. You're going to have crust that is going to be destroyed. No subduction is going to occur here, so you will have no melting of the plate. Therefore, the mountains that are created are not going to be volcanic. Again, you get very strong earthquakes. Because the continents crash together, you get crustal uplift. And the plates tend to be forced upwards, so you tend to get some of the tallest mountains in the world at these continent-to-continent convergences. Here's a continent-to-continent plate boundary from your textbook. And perhaps the best location to see this is India crashing into Asia. The mountain range that's produced by this process is the Himalayan mountains. Here is the Indian-Australian plate crashing into the Eurasia plate, creating this mountain range, the Himalayas. Here's the Himalayas marked by the A, where these two plates, or these two continental plates are coming together and converging and being forced upward to create this mountain range. On that note, this is the end of this lecture, and have a great day.